Okay, this is the lecture number 6 of the ongoing course of structure analysis 2. And this lecture is about the analysis of statically indeterminate frames using the stiffness method. So today we will solve the statically indeterminate frames by using the stiffness procedure. The stiffness method, we studied this for beams already. And today we will study its procedure, and we will repeat its procedure for frames, and then we will apply it on two types of frames, sway frames and non-sway frames. So the topics we will cover today, we will initially introduce this method for the frames. Then we will study some prerequisite topics for using stiffness method. Then we will discuss the types of frames. There are two types of frames, so we will discuss them. Then we will discuss the stepwise procedure for stiffness method. Okay, and then we will analyze some non-sway frames, and then we will end up this lecture by analyzing some sway frames. Okay, so we already have discussed this quite a few times, that the basic aim of analysis using the stiffness method or using any matrix method is to make the solution more systematic. Okay, because the matrix methods are in the form of matrix notations. So when you write your solution in matrices, in the form of matrices, this makes your solution more systematic, and there are less chances of errors. Okay, so in this lecture we will be analyzing the frames using the stiffness method, and you know that the stiffness method is one of matrix methods. So we will be today solving the frames using those matrices, which then we will be putting in the equation which we developed for beams last time using the stiffness method. Okay, so today okay, now if uh, this first advantage is applicable to both flexibility method, also to the stiffness method. Okay, we already discussed this in the flexibility method, that the advantage is that the solution becomes more systematic. Okay. Secondly, the aim of this stiffness method will be to compute reactions at all supports. Okay, to compute reactions at all supports. And this is also one of the very primary aim of any analysis method. Okay, if we are using any analysis method, this remains one of the basic aim. Okay, that you have to find out the reactions at all the supports. And lastly, you have to determine the internal resisting shear forces, the axial forces, and the bending moments at any section of the frame, so that you can be able to draw the shear force and bending moment diagrams for all the members of the frame structure. So these are the three basic aims of the analysis using the stiffness method. Now, what are the prerequisites for using stiffness method? So you should have a good knowledge of matrix algebra. Okay, you should be able to solve matrices. Okay, because we know that the stiffness method involves matrix algebra. Okay, so you should have knowledge of solving matrices. You should also be able to find out the kinematic indeterminacy. Okay, you should also be able to find out the kinematic indeterminacy of the frame members. Okay, and now at the end, you should be able to know the formulas and concepts of fixed inductions. So the fixed inductions, as you know, that in step number 2 and step number 3, we last time we did in beams. So we were actually finding out those fixed end actions corresponding to the specified displacements. So that's why you should be able to know the formulas and also the concept of the fixed end actions. Okay, what are the types of frames? Do you have any problem in this? I think you know matrix algebra, you know the kinematic indeterminacies, and you also know the fixed end actions, how to determine them. So I think we can move forward, okay? If you have any problem, you can ask here. Okay, there are basically two types of frames based on the lateral displacement. Okay, based on the lateral displacement, there are two types of frames. The first type is frames with sway, or in other words, those frames which displace laterally. Those frames which displace laterally. Okay, now what causes that lateral displacement? We will be discussing this in the coming slides. Okay, the second types of frames is that there are some frames which do not deflect or which do not displace laterally. Okay, under the action of the applied load, they do not displace laterally. So they are called frames without sway. So in this lecture, we will be analyzing both sway frames and non-sway frames. Okay. Okay. Now, the sway frames, as we have already discussed, that sway frames are those frames which deflect laterally. Now, this lateral deflection is due to the presence of lateral load. In other words, the presence of lateral load is one of the reasons of lateral deflection of the frames. Okay, or if there is present some unsymmetrical vertical load on the frame members, it can also cause the lateral deflection. Or if the frames themselves are unsymmetrical. So these three are the primary reasons of the lateral deflection of the frames. What are they? Presence of the lateral load. If there is any lateral load present on the frames, it will cause lateral deflection, provided that the support conditions are such that they allow lateral deflection. Or the frames are acted on some, they are acted upon by some unsymmetrical vertical loads. So if the vertical load is acting on the frame members such that they are not symmetrical, okay, so they can also cause lateral deflection. Now let's summarize them again. The first cause is the unsymmetrical loading. Unsymmetrical loading means that there is some eccentricity present at the point where the load is applied. Load is not acting exactly at the middle of the member. Okay, so this causes lateral deflection. Other reason can be there are different end conditions of the columns of the frame. So this also causes the lateral deflection. Third is that the cross sections of the frame members are not uniform. So if we have a frame structure in which there are different cross sections in members, for example, column is of different cross section, beam members in that frame are of different cross sections. So this can also causes lateral deflection. And of course, have horizontal loading. If there is present any horizontal loading on the column of the frame, it will cause the, of course, the lateral deflection. Or if any of the support of the frame settles, so that settlement can also lead to the lateral deflection. So I think this is very much clear to you now. These are a few examples. We can see that here we have a fixed support. Here we have a fixed support, and a uniformly distributed load is acting on this frame member. So this frame member, this frame structure will cannot deflect sideways. Okay, it cannot deflect sideways because we know that there is no lateral load present. Also, there is symmetry in the loading. You see this load is symmetrical. So there is no unsymmetry present in loading. So any of those conditions, none of them is fulfilling here. So that's why this frame is called a non-sway frame. It cannot deflect sideways. Similarly, these other, you can see that here we have 18 kilonewton, but they are acting such that they maintain symmetry. You see this? We have a total 4, so we have a 12 meter this member, and two loads are acting such that they are symmetrical. This load is 4 meters from this end. This load is 4 meters from this end, and they are also at the same distance from the middle of this member. So and there is no horizontal load present. So that's why this is also a non-sway frame. Similarly, if you look at this member, so here we have a horizontal load present, but this horizontal load, it will not cause sideway movement, sideway deflection. What can be the reason for this? Why it will not cause sideway deflection? The reason behind this is that the support. You see, the support condition is such that it will not allow the sideway deflection. Okay, now let's see some examples of this frames with sway. Now you can see that here a load is acting, point load is acting, but this load is at 1 meter distance from this end D, and a 3 meter distance from this end C. So now you can see that it is not acting at the middle of this member. It is a case of unsymmetrical loading. This will cause the sideway deflection of this frame. Also, you can see here that we have this lateral load acting. We have a lateral load acting here also. And here also we have a lateral load acting. So now these all are the examples of the sway frames. Now let's analyze the frames without side sway. Let's first consider those frames which do not deflect laterally, and let's analyze them using the stiffness method. So the procedure, the stepwise procedure for analyzing the frames using the stiffness method, it is the same as we discussed for the beams, but let's quickly go through this. The first step is to find out the kinematic indeterminacy of the frame structure, and then to make the structure kinematically determinate. How can we make it determinate? We can make it determinate by restraining the joints against those displacements. Okay, we have to restrain each joint against against those displacements, and the structure we obtain by doing so is called the restrained structure. Okay, so this is the very initial step of the analysis, that you have to restrain all the joint displacements, and you have to make your structure a restrained structure, which is kinematically determinate. Okay, then in the second step, what we do, in the second step, we apply the actual external load. We apply the actual external load on this basic kinematically determinate structure, which we obtained in the step number 1. So now we apply the actual external load on this structure, and then we find out the fixed end actions. We find out the fixed end actions, and those fixed end actions should correspond to the locations of the specified displacements. Okay, they should correspond to the locations of the specified displacements, and we call those fixed end actions as the values of our aerial matrix. You know this very well from the beams. Okay, so we call those the values of our aerial matrix. Now, in the step number 3, what we do, we apply a unit value of displacement. We apply a unit value of displacement at any of the specified displacement location, and then we again find out the fixed end actions due to the application of that unit displacement. Okay, and we name those fixed end actions as the values of the stiffness coefficient matrix. Okay, so what we do actually, we apply a unit displacement corresponding to location number 1, and then we find out the fixed end actions corresponding to location number 1, location number 2, or location number n, if there are n number of displacements specified initially. Okay, so this way, then again we apply a unit displacement at the location number 2, and again we find out the fixed end actions at the location number 1, location number 2, and at all other specified locations, which are produced by that unit displacement at location number 2. Okay, and so on. So this way we get our stiffness coefficient matrix. Then in the step number 4, what you do, you simply plug in your matrices here in this equation. So to find out the values of this D matrix. Now this is the stiffness matrix which is obtained from the step number 3. And this aerial is the matrix which you obtained from the step number 2. And what is the AD matrix? You know that the actions corresponding to the specified displacements. So the external actions, the external moment, or if there is any external horizontal or vertical action acting at your specified displacement, so you will choose that as your AD matrix value. Okay, so at the end, then you compute the once you get the value of this D matrix, in using this D matrix, you can then compute the member end actions in the step number 5. Now let's solve an example problem on this. In this problem, we are asked to analyze this frame using the stiffness method. And if you look at this frame, it consists of 2 frame members. This member AB, it is of 10 feet length, and this member BC, it is of 12 feet length. This member BC is acted upon by this 2 kip per foot uniformly distributed load. And EI is constant for both the members. EI remains constant. Now, the very first step is to find out the kinematic indeterminacy of this frame structure. Now, if you look at this frame structure, I don't need to go into the formulas, and I don't need to write that formula and then to find it. I just, by looking at this frame structure, I should know that what where there is the possibility of deflection. If I start with this support A, so I know this is a fixed support, and at fixed support uh, there is no rotation possible, there is no deflection possible along the x, also there is no deflection possible along the y-axis. So it means that there is no degree of freedom at this support A. Now I move to the support B, and if I look at this support, so I should know that if this 2 kip per foot uniformly distributed load is acting on this member, and this member is connected at this point B. So now what will happen to this point B when this load acts on this member? This will rotate this point. This will rotate this point. Okay, this will rotate this point. It means that we have theta. We have one rotation possible at this point B, and this point is a point where this member BC and member AB are connected. So this point will rotate, and that rotation is due to this load applied on member BC. Okay, so it means that I got my first theta. So it means my here I will have my first D1. Now if I come here to this support C, so I can see that if I take this support as a hinge support, so it means that this the member at this point will rotate. It means that we have now the second degree of freedom here, theta 2. Even if you take this support as roller support, but if you neglect the axial effects, so still you will have only this rotation possible at this support. It means that the kinematic indeterminacy of this frame structure is 2 degrees. Okay, how it is 2 degrees? So now we know that one rotation is at this point B. Point B is rotating under this load, and also this point C is rotating under this load. So these two are the kinematic indeterminacies. Okay. Okay. Now, in the next step, we specify these displacements by D1. The first displacement, the first rotation by D1. This is now our unknown, first unknown, and the second rotation by this D2, which is now our second unknown. So the aim of our analysis will be initially to find out the values of D1 and D2. D1 is corresponding to the rotation at point B or at joint B, and D2 is the moment corresponding to, or the action corresponding to, this rotation at point C. Now, what are the values of the AD matrix? Now we know that what is AD1? AD1 is the action, external action corresponding to D1. Now, where is our D1 acting? Our D1 is acting at this point B. So, is there acting any external moment at this point? No, there is no external moment acting at this point. It means the AD1 value is 0. Now I go to the second point, which is J2. And I observe here that is there any external moment acting at this point? No, there is no external moment acting at this point. It means that the AD2 value is also 0. It means that the AD matrix becomes 0 because there is no external moment. In other words, there is no external action acting corresponding to our specified displacements D1 and D2. Okay, now in the next step, we have to restrain our members. We have to restrain them against the displacements. So how many displacements we have specified? We have specified 2 displacements, D1 and D2. D1 was at this point B. D2 was at this point C. So now I want to restrain this point P against the rotation. So how can I restrain this? I can restrain this by fixing this this point P. In other words, I am restraining this point from rotating here, okay, under the load. Okay, now where was our D2? D2 was our at point C. Now I make it fixed. Why I make it fixed? Initially we had a hinge here. Now I replace this hinge by this fixed support. Why? Because I want to restrain this rotation, which was possible in case of this hinge support. So now in case of fixed support, there is no rotation possible. So now I have changed the conditions at these points B and C such that now there is no rotation possible at these points. So now this becomes my restrained structure. Now this becomes my restrained structure. I also call this, I can also call this a kinematically determinate structure because now the degree of kinematic indeterminacy is 0 because now there is no rotation possible. Okay, now in the step number 2, what we are going to do, we are going to apply the external load. What was the external load acting? So on the member BC, there was a 2 kip/foot uniformly distributed load. And on the member AB, there was no external load acting. So now let's find out the fixed end actions in these members, member AB and member BC. I want to find out the fixed end actions. And those fixed end actions are coming from the externally applied load. So if I look at this member BC, I have this 2 kip/foot load acting. So from this 2 kip/foot load, the fixed end moment at this end and at this end, it will be equal to WL square divided by 12. W is the magnitude of this uniformly distributed load, and this 12 is there in the formula. L is the length of this member. So the length is 12. It means 24 times 12 squared divided by 12. This becomes your fixed end moments at this point B and this point C, which is 24 fit. Okay, what are the vertical reactions? The vertical reactions are WL/2. Okay, WL/2. So 12 into 2 is 24 divided by 2 is 12. This is also 12. Now, if you look at this member BAB, there is no external load acting. So, but we can transfer this 12 kip vertical load as this member is resting on this member. So now this 12 kip load will be transferred to this member, and it will be resisted here. It will be resisted here. There is no horizontal load acting here. Here also we will have 0 kip horizontal or lateral load. And what about the moments? Now there is no moment possible. There is no moment possible here. Why there is no moment here? Because we don't have any load acting on this member, which causes this fixed end moment. If we want to calculate the values of our ADL matrix, so the ADL1 value should correspond to the specified location number 1, and specified location consists of this B, which is shared between the member AB and member BC. So now the ADL1 value will be the moments. So 0 kip moment here and 24 kip fit moment here, and this is anti-clockwise. So what will be the ADL1 value? ADL1 value will be minus 24 kip fit. Okay. What will be the ADL2 value? The ADL2 value will correspond to the location number 2, as the displacement was the rotation there, and the action corresponding to displacement is a moment. That's why we will only pick the moment values here, okay? Only the fixed end moments we will be picking. So now the ADL2 will be the fixed end moment corresponding to this location number 2, and which is clockwise. So this is positive 24 kip fit. So now this becomes my ADL matrix. This becomes my ADL matrix. Okay. Now in the next step, step number 3, I am going to find out the values of the stiffness coefficients. So we already discussed that I have to apply a unit rotation. In the first step, I will apply a unit rotation at location number 1, and due to that unit rotation, there will be induced some moments in the members, and then I have to find out the values of the fixed end moments which are due to this unit rotation. So I have to find those fixed end moments first at the location number 1, and then at location number 2. Okay, so I will call it S11 coefficient and S21 coefficient. A1 due to 1, and A at location 2 due to unit displacement at location number 1. So now let's do this. This is the location number 1. I need to apply a unit displacement, and as we know that displacement in this case is a rotation, so now we give a rotation. We give a value of theta equals to 1 here. So when you apply a unit rotation here at this point B, which is shared between the member AB and member BC, so what it will cause? It will cause this moment. It will cause this moment. Okay. It will cause this moment which is induced in this member. Also, it will cause the moment induced in this member. So now, the value of this induced moment at the near end is 4EI over 12, 4EI theta over 12, and theta is equal to 1 in this case, so it becomes 4EI over 12. And at the far end, it is equal to 2EI theta over L. And the compensating reactions, which should be in the opposite sense, these induced moments. Now their values are 6 times EI theta over L square. Okay, as theta is equal to 1, so this becomes 6 times EI divided by this 12 square, which is the length of this member. Now similarly, the moments induced here at the near end is 4EI over 10, as the length of the member is 10, and at the far end it is 2EI over 10. Similarly, these reactions are 6 times EI theta divided by this L square, which is 10 square in this case. And now, from where is this vertical reaction coming? This vertical reaction is coming from this member. This member A, this member BC, in fact. How? We know that this is 6 times EI divided by 12 square. And here at this end, we also have a 6 times EI divided by 12 square. And as it is upward, so here it will be downward at this end of this member. Now, when you transfer this to this member, it will become upward. And then when you resist it at this end, it will become downward. So this is this vertical reaction which is coming from this member. Okay, so I think this is very simple. Okay, now how can I pick my values, S11 and S21? The first value, the first coefficient will be S1 and 1. Why 1? This first one is showing this location, 1. It means that it is that location where you are going to find out the fixed end action. This fixed end action, where you are going to take those fixed end actions. This first value gives you that location. And the second value, this gives you the location where your unit displacement is applied. So where is the unit displacement applied in this case? The unit displacement is applied at location 1. These are our two coordinates, coordinate number 1, coordinate number 2. So S11 means at coordinate 1, fixed end actions at coordinate 1 due to displacement applied at coordinate 1. And what will be the value of S11? The value of S11 will be, now if you see this coordinate 1 is shared between these two members BC and member AB. Member BC and member AB. So now you have to take both moments, or moments in both members. The first moment is this 4EI over 12, and the second moment is this 4EI over 10. So as both are clockwise, so both of them will be added, and the value will be 4EI over 12 plus 4EI over 10. This will be the value of S11. We will see this on the next slide. Now, what will be the value? What will be the next value I'm getting from this slide? The next value I'm getting from this slide is S21. Now, what is this 2 showing? This 2 is showing this coordinate number 2. Now, and this one is showing the displacement location, the unit displacement location. So now our unit displacement was applied at coordinate 1, and due to this unit displacement, the fixed end moment coming at the location number 2 is 2EI over 12. So this becomes my, and this is clockwise, this will be positive. So this will be 2EI over 12. Now, let's have a look at this. This is our S11 value. Now you can see that 4EI over 12 plus 4EI over 10. And what is our S21 value? This is 2EI over 12. So these are the two coefficients we obtained from this step. Now in the next step, we are going now to apply a unit displacement at a location number 2, at coordinate number 2. So now I apply a clockwise rotation at now this 2, coordinate 2, and due to this rotation, now the fixed end actions at the near end and at the far end are shown here. At the near end, we have 4EI theta over L, and at the far end, we have 2EI theta over L. So now what values I'm getting, and similarly, these are the reactions. Now, what coefficients I'm getting from this slide? I'm getting S1, 2, 8, 1, 8 coordinate 1, due to displacement applied at coordinate 2. This value, and what will be this value? This value will be equal to this 2EI over 12. Why I'm not taking any moment value from this member? Because there is no moment induced in this member due to this clockwise rotation at the point C. So the value will be 2EI over 12. Clockwise, so positive. Now, what will be the value of S, next value, S22, which means 8 coordinate 2, fixed in action 8 coordinate 2 due to a unit displacement 8 coordinate 2. So this value will be equal to, this is clockwise, so this is 4EI over 12, positive. So you can see it here now. S12 is 2EI over 12, S22 is 4EI over 12. So this way, now I have obtained all the values of my stiffness coefficients, and this becomes my stiffness coefficient matrix. Now, in the step number 4, I need to put all those values now which I obtained from the previous steps here in the, now I have to put them in this equation. This equation, D, as we have discussed already, that this matrix is unknown. We have to find out the values of the elements of this matrix. This is the stiffness matrix. We just obtained this stiffness matrix. This AD matrix we obtained very initially. AD1 and AD2, both values were 0. And ADL matrix we have already obtained in that step number 2, where we applied the external load. Okay, so now these are the values. This is the stiffness coefficient matrix. These are the AD values, and these are the ADL values, ADL1 and ADL2. So if you solve these matrices, you get the values of D1 and D2 to be equal to 54.40 divided by EI and minus 99.74 divided by EI. Now, this negative sign shows that the assumed direction of D2 needs to be reversed. So we have assumed our D2 to be clockwise, but actually it is anti-clockwise. Now in this step we are going to find out the values of the member end actions by using this equation. In this equation we have to find out the values of this AML matrix and then the AMD matrix, and we already know the values of this D matrix. Okay, so you know very well that how can we compute the AML matrix and AMD matrix from your beams analysis, as we discussed this quite in detail there. But let's repeat it for frames also. Now I'm taking my first member AB, and first I'm specifying the member end actions. By specifying, I mean that I am fixing the directions and locations of my member end actions. Okay, directions and locations. Now, what do we mean by direction? Direction means that I am fixing my first member end action, AM1, to be acting at this end of the member AB, and its direction is upward. Its direction, I'm fixing its direction to be upward, and also its location to be here at the joint A of the member AB. So this becomes my AM1. It is completely your choice that where you want to. You can also start from this end, and you can say that this is my AM1. You can also do this, but remember, if you fix one convention for yourselves and follow that again and again, so it will become easy for you guys, and there will be less chances of mistakes, because later on when we will be doing this computation of AML matrix and AMD matrix, so you don't need to come back to this slide and see that where is my AM1 and where it is directing. Okay, so you should fix your AM values such that you remember that throughout this solution. Okay, so I have now fixed my AM1 to be at this point and acting upward, my AM2 to be this this horizontal and acting rightward, because upward is positive, rightward is positive, and clockwise is also positive. So actually I am fixing my member end actions in positive directions. Okay, so AM3 is this moment and it is acting in the positive direction. Similarly, I am calling this as my AM4, AM5, and AM6. Now, what will be my AML value? So AML1 value will be the value of the action corresponding to your AM1. So your AM1 is this axial force for this member. So your AML1 will also be this axial force for this member. Similarly, your AML2 will be a shear force, as our AM2 is a shear force. And AML3 will be a bending moment, is because our AM3 is a bending moment. Now let's see them. It's just a repetition. Now you can see that this is my now AML1 value. Why at this location? Because I have chosen my AM1 to be at this location. And this is my AML2. This is now my AML3. Similarly, AML4, AML5, and AML6. Now, from where I am getting this member? This member I am getting from the step number 2. What I did in step number 2, I solved the kinematically determinate structure for the actual applied load. Okay, so these are the fixed interactions which you obtain from that step. So as you remember, there is no external load acting on this member, so there is no moment in this member. There is no bending moment, friction moment in this member, this end. Also no value at this end. And this 12 kip is coming from the member DC. Okay. So now what are the values? The values are this value. I will call this value as my AML1 value. This is my AML1 value. What is my AML2? This is my AML2. This is my AML2. The value is 0. What AML3 value is a bending moment. Is there any bending moment at this point? No. This is going to be 0. Similarly, you can take this value of your AML4. You know that our AML4 is assumed to be acting upward. Why it is assumed to be acting upward? Because we have chosen our AM4 to be acting upward in a positive direction. But the action corresponding to this AM4 is acting downward here. So we will take this with negative sign. Very simple. AML5 is this shear force, which is 0. This bending moment, which is also 0. So these are the values. This becomes my AML matrix. Now I go and find out the AMD matrix. Now what I'll be doing in the AMD matrix. In the AMD matrix, now there will be 2 columns. Why 2 columns? Because we have 2 coordinates. The first column will be coming from when the unit displacement will be applied at coordinate number 1. And the second column will be coming from when we will be applying a unit displacement at the coordinate number 2. So in this first step, we applied the unit displacement at the coordinate number 1. And these are the induced moments, and these are the then reactions, corresponding reactions. So what values now I'm going to take? So as you know that our AM1 was here, AM1. It means our AMD1. Our AMD1 should also be here, AMD1. As you know that our AM2 was located here, we located our AM2 to be acting here in this direction. This becomes my AMD2. Similarly, this becomes my AMD3 because it is corresponding to the location of AM3. And similarly, AMD4, AMD5, and AMD6. Now, if you look at this AMD value, there is one other value also, one other subscript, AMD1 and then 1. This other coordinate or this other subscript, it is showing the coordinate value. Other subscript, it is showing the coordinate value. So as you can see that this 1 is repeated with all these AMD values. Why? Because the unit displacement is applied at coordinate 1. Hope now this is very clear. Okay. So this value, this is the value of your AMD11 as it is acting downward, and it is opposite to our assumed direction of our AMD11, so it will be negative. This will be the value of your AMD21, and it will be positive because it is exactly in the direction as we have assumed for our AMD21. Okay. Also, this will be our AMD31, 2i/10, and it will also be clock positive. AMD31 is also clockwise. Okay. Similarly, what will be the value of our AMD41? AMD41 will be the equal to this 6 into EI divided by 12 square, because we have this value here at this end also. But this will be positive. Why? Because when this reaction from this member is transferred to this member, it will be upward. It will be upward. Okay. So and upward is in exact exactly in the same direction as we have assumed for our AMD41. What will be the value of our AMD51? So this will be this one. And it should be negative because it is opposite to the assumed direction of our AMD51. And AMD61 is clockwise. So this value will be AMD61. Now here I don't need to take this value of 4EI/12 with this. Why? Because 4EI/12 is in this member BC. And I am considering only my member AB. Remember, this is very important that you have only to consider the values of the axial shear force and bending moment only in the member AB. Okay, so I am going to take only this moment as my value of AMD61. Okay, now in the next step, I'm going to apply a unit displacement at coordinate number 2. And the values now I'm getting now, you can see that your AMD1 location is same, AMD2, it is the same, AMD3, it is the same as on the previous slide. The only change here is this second subscript, which is now 2. Now, why it is 2 with each of this AMD value? Because now our unit displacement is acted at coordinate number 2. And now, what are the values I'm going to get now? This AMD12 will be 6 times EI/12 square. This is coming from this member. And what will be the value of my AMD22? It will be 0. There is no shear force acting here. AMD32, it will also be 0 because there is no moment. Similarly, AMD42 will have a value of 6 times EI/12 square. But AMD52, AMD62, they both will be 0. So now this becomes our AMD matrix. This is the first column, which is coming from when a unit displacement was applied at coordinate number 1. And this is the second column, which is coming from that step when we applied the unit displacement at coordinate number 2. Okay, now we need to put all those values in our this in our this equation of this AML matrix, AMD matrix, and the D matrix we already obtained initially. So now when you solve these matrices, you come up with these values of your member inductions for member AB. So now you need to draw the shear force and the bending moment diagram for this member AB. Okay, this is the shear force and the bending moment diagram. And now we need to repeat the same for our member number 2, which is member BC. Okay. So now what you need to do, you need to simply specify your AM values first. And then you need to find out the values of your AML matrix. Okay, what will be my AML1 value? This will be this one. So this is 0 here. There is no this axial force here. And similarly, you can get your AML2 value. Why 12 kip? Because why positive? Because this is upward. Similarly, your AML3 value, AML4 value, which is 0, AML5 value, and AML6 value. You can get from this one. Now, similarly, as we did for the previous member, you can repeat the same for your this member. Okay, you can see this. So this is your AMD matrix, and then you solve it here, and you get these values as your member and actions, and then you draw the shear force and bending moment diagram. This is the combined shear force and bending moment diagram. So this was all about the problem number 1. I hope this is very clear to you. Now let's quickly solve another problem on this stiffness method. If you have any question till now, you can ask now, or we can proceed to this next problem. Now, in this problem, I will be going a bit quicker because it is exact repetition of the previous problem, but there will be changes, very little changes. Okay,